Good afternoon. So in the last class, we have talked about the paging. So what do we mean by paging is, in memory management, we have seen in the last so many classes that there are two types of memory, where the hard disk, what we store everything is one part of memory. Another one it is a small one which is present in the CPU. So the paging, what we do here is the paging is a memory management scheme. It is one type of scheme. So what that is doing, that permits the physical address of the space of a process to be non-contiguous. So what do we mean by like this is, so for which we are calling it as a, we have seen in the last classes, for some things we are calling it as a logical address, and for some things we are calling it as a physical address. For the memory which is there in your CPU, we are calling it as a logical address, and the memory which is present in a physical is called as a physical address. That's what we see here. What we do paging is, so to store everything, we have divided our hard disk into different forms. So one you can see here. One second. I'll share. Sorry. Okay. So here you can see how the files in your drive will be there. Suppose if I click on my PC, how the data are. So you can see here, the first C drive is 465 GB, means it will be around 500 GB. So more space is given for C. And later, so it is giving how much is used, how much is free. In the same way, for rest of things, you can see how much is used, how much is present. So that's what here we can see. Okay. So the same way here we can see paging. Paging is a memory management scheme that permits the physical address space of the process to be non-contiguous. Means, so the memory will not be in a continuous, and we cannot say that I will shift. So that's what a paging says. Paging avoid the problem of fitting. So suppose you think that there are 10 people in the second semester, and all 10 people are sitting, and one more student comes 21st. Then I cannot ask the first person to go shift. I cannot ask all 20 people to shift back. Instead of that, what is the option given to us? We'll bring one more chair and ask that extra person to come and sit. Same way here, even in paging also, what we do, the basic method. So how the memory, how to store is divided. So that's the same thing here. Physical memory. Where is the physical memory? Physical memory is in a hard disk. So in the hard disk, whatever memory is there, that is called as a physical memory. And how we have made that hard disk? So physical memory is broken into fixed size blocks. So what we do, we divide the different blocks and call it as a frame. Okay. So let me give you one example where you have your bags. What bag? You're carrying your books, your pens, everything. So what you do? Can you keep wherever you're keeping pens, books, and wherever you're keeping pens, can you keep it in a box? Okay. For pen, if you give big size also okay. But for the books, can you keep the books in the place of pen? It's very difficult. It cannot keep because it is not fitting. Your book cannot fit in the pen's place. That's the same way here also. What we do is physical memory is broken into fixed blocks. So what is done? Fixed blocks. It is being present, and what that fixed blocks we are calling that as a frames. Where are these frames? Frames are present in the hard disk. So the hard disk in the operating system terminology, what we call it as a physical memory. Then what is logical memory? Logical memory is CPU's memory. So logical memory is also broken into blocks of same size called pages. So what we call the logical memory, we call Even there also the memory is divided into equal thing, and that is what is called as a page. So when a process is to be executed, its pages are loaded into any available memory frames from the backing store. So now we have something called as a backing store. Means backup we keep everything. So the backing store is divided into fixed size blocks that are of same size as that of the frames. So in the same way, hardware support for paging is illustrated. So every address generated by CPU is divided into two parts. One is page number and one is page offset. So the page number is used as an index into a page table. The page table contains the base address of each page in a physical memory. The base address is combined with the page offset to define the physical memory address that is sent to the memory unit. So the paging model we'll see in the next slide. The size, so everything, whatever we keep, the size of the page is typically of power of 2. If the size of logical address space is 2m and the page size is 2n addressing units, so then the first m to n bytes of logical address indicates page number and the next n bits is a offset. So we'll see how we do it. So you can see in this diagram, this is the paging hardware. So you can see the logical address is from CPU and the physical address is from a memory, that is physical memory or your hard disk. Okay, we have to map all this. We have one more thing called as a page table. So what is there in page table is, so you can see P. P stands for page number. D stands for offset. So what is offset? Offset means from where to where is one page. From where to where is second page. So you can see, so if I, in the same way, if you see the PPTs, what is their page, PPT numbers also we have, 1, 2, 3 like that. So if I say how many pages do chapter 2 or unit 3 is having. So I'll say 125 slides are there in a unit 3. Means what? So much is the content of unit 3. Same way here, the CPU will be having two logical address. One is CPU is logical address and physical address in memory. So what is P stands for? P stands for a page number. What is D stands for? Page offset. So you can see in a page table, we keep all these details. So F is the offset or from where the P completed. Next, what is a page? So it will be clear in the next slide, this one. Okay. So you can see here, what we can see here, we have a three types, what we have seen in the last slide. Logical memory, page table and physical memory. So what is logical memory? In logical memory, we have how many pages at least in this slide? 0, 1, 2 and 3. How many pages we have? 4 pages. What are the numbers given for those pages? Page 0, page 1, page 2, page 3. Then in page table, so 0, 1, 2, 3 are the page table index. So 1 is what? 0 and 1. 1, 4, 2, 3, 3, 7. What it stands is, so at a place of 0, page number 0, at the place, at a page 0, what is the place in the physical memory? So you can see at the place 0, 1. So at the place 1, what we have? 4. So you can see page 0 is in one place. You can see this side of the table where at the place 1 is a page 0. At the place 1, in page table, you can see 4. 4 stands for page 1. At which place is page 2? 3. 3 at place 3, page 2 is there. At 7, page 3 is there. That's what it says. What is the address of physical memory and what is the address of logical memory? So to keep track both of this, we have one more table called as a page table. What is there in page table? Address of the physical memory and address of index, address of the logical memory. What are the pages we have in this slide? There are 4 pages. Page 0, page 1, page 2, page 3. So where are these page 0 placed in main memory or physical memory? in page 0 is placed in the address in the frame 1 of physical memory. Page 2 is stored in frame 3 of physical memory. Where is page 1? Page 1 is stored or placed in the frame number 4 of physical memory. Where is page 3? Page 3 is placed in the place of the frame 7 of the physical memory. So this is what the explanation about a paging model of logical and physical memory. So what is physical memory? Where do the physical memory will be there? Physical memory is present in a hard disk. So how this physical memory is divided? It is divided into frames. How are frames? Frames are of equal blocks. What is frame? Frame is a equal block. Same way, what is logical memory? A CPU's memory is called as a logical memory. How are these divided? These are divided into pages. So what is this? Each one block in a logical memory is called as a page. So to map these two, what we are using one table called as a page table. What is there in the page table? The index of logical table, logical memory, and the frame number of the physical memory is present in the page table. What is present in the page table? Page table is having the frame numbers and page numbers of logical memory and physical memory. Okay, so let us consider one example. So you can see in this example, so what does the logical memory have? It starts from 0 to 15. How each page, what is the size of each page? So normally, what is the page size? How, in which page do you take printout? In which page do you take printout? Yes, anyone? In which page do we take printouts? A4, A3, index sheets. Which page do we take printouts? Okay. So here consider a page size of 4 bytes and physical memory of 32 bytes. That is 8 pages as shown in the figure 3.7. We will see now how the user view of memory can be mapped to a physical memory. So logical address 0. So you can see here the logical address is 0. So what is the size of this? 4 bytes each. So what is the page table? 0 and 5. In which place 5 is? What is the 5? 5 is the physical address. How to find out this physical address? 5 into 4 is how much? 20. 20 plus 0 is 20. So at the frame 20, A, B, C, D are present. What is A, B, C, D? That is 0, 1, 2, 3 are present in the logical memory. That's what here. The logical address 0 is a page 0, offset 0, indexing into the number into the page table. We find that page 0 is offset. Indexing into a page table, we find that page 0 is in the frame 5, thus logical address 0 maps to physical address. So 20 equals to 5 into 4 plus 0. What is this 5? 5 is the place of a physical into 4. What is 4? 4 bytes. 5 into 4 is 20 plus what is 0? 0 is offset. So that's how we try to calculate what is the present in the page table. What is the address of physical table? What is the address of the page table? Okay, logical address 3. Page 0, offset 3 maps to physical address. So that's what 5 into 4 plus 3. Oh, this 23. So you can see what is the thing they are asking. They are asking us to find out logical address 3. What is logical address 3? Logical address 3 means logical address 3 is in the page 0 only. In page 0 only the logical address is there. So what is the offset 3? Yes, 5 into 4 plus 3. So is what? 23. So logical address 3. The same way, logical address 4, that is 4 means page 1, offset 0. So, what is a size, page table size? 6. Frame size is 6. So, 6 into 4 plus 0 is 24. So, that's how we try to calculate this paging example. So, when paging is used, there will not be external fragmentation. So, what is external fragmentation? External fragmentation means memory is free. Some memory is free here, some memory is free here, some memory is free here. But I cannot use completely because of external fragmentation. That will be ruled out in the paging. Any frame can be allocated to a process that needs it. However, some internal fragmentation will be there. To reduce it, small sized page are preferable, but more number of pages will lead to many entries in page table and hence much overhead. So optimum selection of size of each page is essential. When a process needs to be executed, its size represents in terms of number of pages is examined. Each page of process needs one frame. Thus, if the process requires n pages, at least n frames must be available in the memory. How do we support this with the hardware? So hardware support, each operating system has its own method for storing page table. In the simplest case, the page table is implemented as a set of dedicated registers. So another method which we use here is a page table is kept in the main memory and page table base register points to the page table. Same way how we have a page table, so in the same way we can use one more table in the register. That is what is called as a PTBR. What is this PTBR? Page table base register. In this scheme, every data and instruction requires two memory access. One for page table and one for data or instruction. This double access problem can be solved by using a special fast lookup hardware cache called as a associative memory or translation look aside buffer, TLB. What is this TLB stands for? Translation look aside buffer. The TLB is associative high speed memory. Each entry in the TLB consists of two parts, a key and a value. The TLB is used with page table in the following ways. How do this TLB is used? TLB contains only a few of the page table entries. When a logical address is generated by the CPU, its page number is represented to the TLB. If the page number is found, its frame number is immediately available and used to access memory. If the page number is not TLB, a memory reference to the page table must be made. When the frame number is obtained, we can use an access memory. So that's what here you can see. One extra thing we are using, that is what is called as a TLB. So in TLB, page numbers and frame numbers are also there. From where do we get the page numbers? Page numbers we are getting from a CPU. From where do we get the frame numbers? We are getting the frame numbers from a physical memory. So to do all this, we require a protection. So why do we require protection? Same way in our laptops, to protect it from unauthorized user. For anything we use, we have a login ID and passwords. So in the same way, antivirus is also there to protect from a unwanted virus to be attacking our system. So in the same way, protection is also required for memory. So in paging technique, protection bits are associated with each frame to keep are kept in the page table. So protection. So each we have some bits, right? In out of so many bits, one bit is reserved for protection bit. So this will help memory protection. So sometimes we say we open some file and they say it is read only. I cannot edit. So that's what, for that bit we are using the extra bit called, that bit is called as a protection. So sometimes you can make that bit read write or read only. That's what read and write or read only. While referring the page table to get a frame number, the protection bits are also checked. An attempt to write a read-only page causes hardware trap to OS. Another bit attached to page table is valid and invalid bit. So I should check whether it is a valid or invalid. When this bit is set to valid, it indicates that the respective page is in the logical address space of the process and hence it is legal or valid page. If this bit is set to invalid, the page is not in the logical address space of the process. So that's what the protection says to us. So doing this, we have a, structure of a page table. The most common technique for structuring the page table are hierarchical paging, hashed page table, and inverted page table. We'll see all these three one by one. First one is a hierarchical page. So what do we mean by hierarchy? Hierarchy means, suppose if we consider grandfather, father, son. What is the hierarchy here? Grandfather is first, next hierarchy is father, next is a son. So anyway, here we have something called as a hierarchy of page. We'll see what we are doing in a hierarchical page. Most modern computer systems support a large logical address space. In such an environment, the page table itself becomes excessively large. For example, consider a system with a 32-bit logical address space. If the page size in such a system is 4 KB, 2 to the power of 12, then a page table may consist of up to 1 million entries, that is 2 to the power of 32 divided by 2 to the power of 12. To avoid this problem, one solution is to divide the pages into smaller pieces. To do this, we have a two-level paging algorithm can be used. Here, the page table itself is page as shown in the figure. You can see to avoid in a hierarchical thing, we have a two-level paging. So two-level page table scheme says that the outer page table and a page table and a memory. So here you can see, so one, how the pages are divided. It is divided into 1 to 500, 100 to 708. So like this, these are the different pages are divided. And each is mapped to where it is actually present in the memory space. Next, we move on to the hashed page table. A common approach of handling address space larger than 32 bits is used a hashed page table. So now when you buy a thing, when you buy any new system or laptops, we are increasing with the bits. Earlier we were having only a 32 bits. Now we have a 64 bit, even more than 64, 128 bits. So like this, day by day, as the technology is increasing, as we require more data, that's what the storage is also increasing. Now you can see 1 terabyte, 2 terabyte is also existing. So how to handle such huge data to store in memory? If I'm storing, how to trace them, where, what it is. So for that reason, we are using all these technologies. One is a hash table. So each entry in the hash table consists an array of linked list that hash to a small location. Each node in a linked list consists of three fields: the virtual page number, the value of a mapped page frame, a pointer to the next element in the linked list. So what is a linked list? Linked list is one node. What it will be having? It will be having its address as well as behind next address. What is a next node's address that is present in the one particular node, and this we are calling it as a linked list that is used in the hash table. So how does this algorithm works? So the virtual page number is a virtual address in a hash table into the hash table. The virtual page number is compared to the first field of the first node in the linked list. If there is a match, the corresponding page frame is used from the desired physical address. If there is no match, subsequent node in the linked list are searched for a matching virtual page number. So what we are doing, it's start searching. So it will start searching from the first node and keeps going on. If it is matching, it will find. If it is not matching, it keeps going to the next like this. That's what a hash table will be done. That's what here you can see the scheme. The scheme of shown logical address and physical address. So hash function is there, hash table. So that's what here you can see. QS, that is one linked list. Next PR is one more node. So after one node is attached to the next node is attached to the next. Like this, it keeps adding a linked list. Next is inverted page table. So it is obvious that each process has its own page table, and every page table has only entry for each page. We know that the page represents logical or virtual address. It is the operating system which converts the logical address into a physical address later. So who will take care of converting what is there in hard disk? If I want to use one Java program or data structure program or CM program, where is my data? You keep your create one folder and store there. And who will be mapping this with the CPU? That will be taken care by the operating system. As a page table contains millions of entries, it is burden on OS to convert everything into a physical address. To avoid this problem, inverted page table is used. This table contains one entry for each real physical frame of memory rather than for logical memory. Hence, only one page table is sufficient for the system. As each process has its own address space, another entity specifies process identifier in its address. Space is used as shown in the diagram. So we'll see in the next slide how the page inverted hash table is used. So how it is working? Working is explained below. The page table consists PID. So what is PID? ID of each process. So in the same way, you people also have a student ID. When you have BMSIT students ID, you will be allowed into a BMSIT campus. Same way here. So we have a PID, that is a identification, and a page number. So if I have 100 pages, to identify which page should come next, which page should come next, if you have taken printout, and if you have forgot to give a page number, then it will be very difficult for you to sort out. If you have given page number, it will be easy for you to sort your 100 pages. That's the reason we require a page number. The CPU generates logical address containing PID, each number and a offset. The pair PID and page number is searched for in the page table. If the match is found at the ith entry, the physical address will be I, offset. The match is not found, illegal address access error occurs. That's what here you can see. So what are the two things we keep searching? One is PID and one more thing is called as a page number. We search for both. So I search for Chaitra and what is the address where she is staying. I search for both and see whether she is the same Chaitra or different Chaitra. Same way here, CPU and a physical memory will also be searched for address, ID and a page number. So that's what here you can see. Process 1, process 2, process 3. So suppose if I have 3 processes and each one has a P1 page table for P1, page table for P2, page table for P3. So some options are there along with that data. So it would ED1, 2, 3 like that data 1. So the same way you may have any number of tables, any number of data, but each process will be having a separate page table. So page table 1, where the page table is 3, 4, 6, 1. So the process 2 is present in a 3, 4, 6, 7. So that's what here, sharing of code in a paging environment. How do we share in the same environment? So this diagram depicts you, there are 3 processes, P1, P2, P3. And each process have a page table for P1, page table for P2, page table for P3. And where these are stored. So data 1 of the processor P1 is stored at the place 1. And in the same way, data 2 of processor P2 is stored in the place 7. And in the same way, data of P3, it is stored in a 2. So that's how the data is present in the physical memory. What is physical memory? Physical memory means your hard disk. So what is the address of all this? Data 1 is present at the frame 1. Data 2 is present at the frame 7. Data 3 is present at the frame 2. So this picture depicts us where are the data. And ED1 is present in the frame 3. That's what you can see. ED1 is present in the physical memory 3. Where is ED2? ED2 is present in the physical memory 4. Where is ED3 present? Is present in the 6. So that's how the data for all these processors are shared. Shared pages. Sometimes same way how you have in your compiler built-in functions. So header files hash include stdio.h. So stdio.h can be shared by so many programs. Any number of programs you write, all those are shared. Same way here, what is this shared pages? A paging technique is useful in time sharing environment. So time, the same way here you have a calendar, we have a timetable where each hour each person has to take. So today morning was first hour, after that you have lab. So today in the afternoon, one first hour is fine, next hour is up. Means what we have done, timing is shared from 8:30 to 3:30. So that's what page technique is. Some of the processor have re-entertained code. That is, once they start execution, the code will not change. In such situation, page can be shared. Consider an example. Assume that 400, so assume that 40 users are using a text editor at a time. So suppose you think that all of you have to do mini project and you have to start doing your report. In your class, you are 53, but 40 of you are using a text, means doing your project. Let the text editor consist of 150 KB of code and 50 KB of data space. What is the size of the memory what we are using? We need 8000 KB for 40 users. So each one requires 150 KB of code and 50 for data space. So then for 40 users, how much data we require? We require 80,000 KB for 40 users. As a text editor is re-entertained, only one copy of the editor needs to be kept in the physical memory and it can be shared among all the users. So there can be only one copy and the same copy can be shared between so many people. But the data space could be different for every user. This is depicted in the figure. So we'll see in the next how this is being done. In this example, the size of each page is taken as 50 KB. Sometimes, now if I say Anu is required 50 KB, Chaitra is required 100. So then these two I cannot share because she wants 50 and she wants 100. How can I share? It is not possible to share. Such sharing techniques can be applied for compiler, Windows, runtime libraries, database, etc. So only in such type where it is possible for sharing, only then we can apply or use. So next we'll see about segmentation. So what do we mean by segmentation? Segmentation means dividing your memory into equal parts. So in paging, we have observed that user view of memory and actual physical memory are different. So user view of memory is mapped to a physical memory. So what we are doing here, how do we map? We are mapping dividing the memory into a different segmentation. Means segment means what? Divide. So how we are dividing? Again, it's based how your data is. Okay. So that's what here. The basic method, we user do not think memory as a linear array of files. So I am user, your user. How many programs you have stored? You would have stored the Java programs, you have stored data structure program, you have stored CN program. Instead, user view memory as a collection of variable side segment. So segment, it may be variable. So how your difference between structure and unit? What is structure? Structure is fixed. So if what is the size given? Integer 2 byte, float so much. So it will add everything and it will fix so much memory. What is union is doing? What whichever is bigger size, that will be only one used. So in same way here also, variable size means based on what size of memory you want, you can vary with no necessary ordering among segment as shown in the figure. We'll see in the next slide what is a figure. For example, we think of a program as a main memory with a set of subroutine, procedure, functions or modules. There may also be various data structures, that is table, array, stack, variables and so on. Each of these modules or data element is referred to by name. We do not bother which module has is stored before, after other module. So you can see here the segmentation of this. So how each one segmentation is a memory management scheme that supports user view of a memory. A logical address space is a collection of segments. Each address is specified in terms of segment number and the offset within the segment. So you can see here in this diagram, this is a user view of the program. So logical address space, you are using the subroutine, you are using a stack, you are using the symbol table, you want one function called as a square root and you are using the main program. For all these, it is divided, the memory is divided to give each of this. This we are calling it as a segment. How is with this with respect to hardware? So here a two-dimensional user-defined address are mapped into one-dimensional physical address. This mapping is affected by a segment table. So each entry in the segment table has segment base and segment limit. So what is segment base? How is your array? So you just say A of 10. So what is A1? A1 is a starting address. What is A9, A10? Last address. Same way here. Segment base contains the starting physical address where the segment resides in the memory. What is segment limit? The limit for the segment. How many I have to divide. A logical address consists of two parts. A segment number S and an offset D. What is S? S stands for segment number. What is offset? A difference from where to where. So that's what the offset is. The offset D of a logical address must be between 0 and the segment limit. If it is not, we trap the operating system. If this offset is legal, it is added to the segment base to produce the address in the physical memory of a desired table. The segment table is thus essentially an array of base limit register pair. The structure is given here. So you can see here the segment table, how we have a page table. In the same way, we are using the segment table. Segment table, what are the two things we have? Segment number and the D is a offset. So again in segment table, what we have? Limit. What is the size? What is the base address? We check whether it is within the limit, then yes. If no, then close it. So that's what this says. What is CPU? What is a physical memory? CPU is the temporary memory which is required for CPU. What is physical address? A hard disk which is used. Can we consider an example? Consider the situation shown in the figure 3.5. We have 5 segments. How many segments? We have 5 segments. Numbered starts from segment 1, 2, 3 and 4. How many? We have 5. So 5 segments are there. The segment table has a separate entry for each table. So each one will be having a each entry. It is given beginning address of the segment in the physical memory or a base address and the length of that segment. For example, segment 2 is 400 bytes long, begins at the location 4300. You can see in this diagram how many segments. Routine was one segment, stack, symbol table, main program and sort. So segment 0 is subroutine, segment 1 is square root, segment 2 is main memory, segment 3 is stack, segment 4 is symbol table. All these are present in the segment table. So limit 0, 1, 2, 3, 4 are 5 segments. What is the limit? 1000 per segment. And where it is stored? It is stored at 1400. And what is 1? Segment 1 is square root function. What is the limit? 400. What is the base address, or what is the address of 3200? And where it is present, that's what 606300. So that's how each one will be having its limit and the base address. Base address means what is the actual address where it is stored. Next we move on to a fragmentation. So what do we mean by fragmentation? Dividing. So longer scheduler time must find and allocate memory for all the segment for the user. This situation is similar to paging, except that segments are of variable length, pages are all of same size. So what we do here, so we have seen in a fragmentation two things, external fragmentation and internal fragmentation. External fragmentation means I have memory free, but small one memory is free there, one memory is free here, one memory is here. Means they are not continuous, but still I can because it is not continuous, so I cannot store the data. That was a problem with the external fragmentation. Internal fragmentation, what was the problem? Extra memory we were giving in a internal fragmentation. Same way here, how do we come up with the situation for a segmentation? This situation is similar to paging, except that the segments are of variable length, pages are of same size. So here the pages, whatever we have pages will be of same size. Thus, as with the variable size partition scheme, memory allocation is dynamically storage allocation problem usually solved with the best fit or first fit algorithm. So segmentation may then cause external fragmentation when all blocks of free memory are too small to accommodate a segment. In this case, the process may simply have to wait until more memory. So that's what if I say Chaitra wants some 100 space to keep her moving, and Mithili also wants some space. Anu also wants some space. If all three of you ask the same memory, still Chaitra is using, Mithili is using. Anu asked so much memory which is not available. Then what we have to do? Anu has to wait till Chaitra completes, Mithili completes. If those two people complete and give the memory free, then only Anu can use. The same way here also, unless it is completed, we cannot use. If the CPU scheduler must wait for one process because of a memory allocation problem, it may skip through the CPU queuing queue, looking for a smaller, lower priority process to run. So next we have something called a segmentation with paging. So both paging and segmentation have advantage as well as disadvantage. Same thing. So now the physical classes was one problem. Now online classes is one more problem. So each one of them have their own advantage, their own disadvantage. Here, no external fragmentation. So paging has advantages like no external fragmentation. So we coming to paging, what are the advantages of paging? No external fragmentation, faster allocation. You can allocate or store the data very fast. But same way, segmentation has also advantages like sharing. You can share the thing. Suppose now, if I say in Chaitra house there are two people, his brother and Chaitra, and they have only one laptop. They have to share. So that's what they have to share the thing. Protection. So protect your laptops, our laptops by the antivirus. So the same way here, if you have a Gmail or anything, we are using a password. So these advantages are combined to get a better result. So why can't we combine the paging advantage and segmentation advantage and bring up one solution where we'll be having both of this. So segmentation with paging is explained as below. Instead of an actual memory allocation, the segmentation information includes the address of a page table for the segment. When a program reference a memory location, the offset is translated to a memory address using the page table. The segment can be extended simply by allocating another memory page and adding it to the segment's page table. Also, the logical address space of the process is divided into two partitions, one consisting of segments that are private to that process and the other partition consisting of segments that can be shared among all the process. So demand paging. So suppose how if suppose if I have five resources and all five are in a demand, then who asks me first, they will get the page first. Same way here, the concept of demand paging. So demand paging is one of the technique of implementing virtual memory. So virtual memory is the separation of user logical memory from a physical memory. So demand paging is similar to paging system with swapping. Whenever process need to be executed, only the required page are swapped into memory. This is called as a lazy swapping. As the term swapper has a different meaning, a swapping entire process into memory, another term, pager, is used in discussing of demand paging. So in demand paging, same way you would have seen a Ajax. So instead of online, when a cricket match is being going on, only the current people who are playing, only that score should be changed. Same way here, demand paging, whichever page is asked, only that page will take and execute and save it back. That's what the demand paging says to us. So when a process is to be swapped, in the pager guesses which page will be used before the process is swapped out again. The pager brings only those necessary pages into memory. Hence, it is decreasing the swap time and the amount of physical memory needed. For this purpose, a valid and invalid bit is used. When this bit is valid, it indicates the page is in the memory, whereas the value of the bit is invalid, indicates the page is not on the disk. If the two processes try to access a page which is not in memory, then a page fault occurs. Suppose you think that now if I have so many people, the people who are not there, if I keep calling, means what? That person will not respond. So that same way here, page fault. The paging hardware notice the invalid bit in the page table and cause a trap to the operating system. This trap is the result of failure of operating system to bring a desired page into memory. This error has to be corrected. The procedure for handling this page fault is shown in the figure. We have a figure here. We check an internal table usually kept in the process control block for this process to determine whether the reference was valid or invalid memory access. If the reference was invalid, we terminate the process. If it is a valid, but we have not yet brought this page into memory, it is brought now. We find a free frame, we schedule a disk operation to read the desired page into the newly allocated frame. When the disk read is complete, we modify the internal table kept in the process and the page table to indicate that the page is now in the memory. We restart the function instruction that was interrupted by a illegal address trap. The process can now access the page as though it has been always in the memory. So you can see in this diagram steps in handling the page fault. So if operating system and ask for the load, re-instruction, reference, page is on the backstore or in the free frame. So this is what the explanation steps in handling the page fault. If the page is not available in the memory and you are trying to access, then there will be a problem occurring. That is what is called as a page fault. It is important to, so I'll just complete this and I'll stop. In the next class, we'll start with the process creation. So it is important to realize that because we save the state of the interrupted process, when the page fault occurs, we can restart the process is exactly the same place and the state. In an external situation, a process may start executing with no pages in the memory. So such time an instruction to be executed, page fault occurs and is required page need to be brought into the memory. This situation is called as pure demand paging. That is, no page brought into memory until it is required. So pure demand. So suppose if I ask and if I don't want, then it will be waste. So whenever I really require, then I bring, then that is what is called as a pure demand paging. So I'll stop here and we continue in the next class with the process creation. So by Saturday, I want to complete this module 3. And complete by Saturday. Okay, thank you.
Thank you, ma'am.
Thank you.
Thank